All right, so here we have another example. This is problem 19.38 from the 8th edition of Beer-Johnston. And we have a 9-kilogram uniform rod, AB, attached to springs at here and here, and each of them has a spring constant of 850 newtons per meter, which act in tension or compression. And if the end of the rod is depressed, right, so end of rod A, like we're going to push this down just a tiny bit, and slightly released, determine the frequency of vibration and the amplitude of the angular motion of the rod, knowing that the maximum velocity is 1.1 millimeters per second. So we have a lot of things that we can try to work on here. So first off, let's get the moment of inertia about C. That would be a good thing to do. So we know we have 1/12 ml squared, but we also have to move, that's the center of it is right around there. We need to move, as you see, I have 600 and 360, so we need to move it, I'll just go md squared, right? So the 1/12 is the times 9, and the length of the thing is 0.6 squared. We're going to move it with the mass, and the distance now should be 0.06, right? Because we're going to move it 60 millimeters, must be the distance in between that we're moving the thing squared. And so we get 0.3024 kilogram meter squared. At equilibrium, right, so at static equilibrium, we can find, let's see, I'm trying to picture my own thing. Okay, at static equilibrium, I'm going to draw this in here. This will help me later on. Like I would have gotten to the state at one point and maybe got a little stuck with too many terms. So we're just going to take a look at with a assumed amount of compression, right? So let's pull this end down and have this some end compression right here. So this is pulling upwards and this is pushing downwards. This is the force of the spring at B, and here's the force of the spring at A. And we'll say here is like a small angle that has been put into here. Yeah, and well, I also decided that this right here was the deflection, static deflection at B, and this distance right here, sorry about that, is the static deflection of A. So taking the sum of the moments equal to 0, this is the static condition right here. So this is the static at equilibrium, right? So, I see. Okay, let me take that back for a second. We also have, so here you go. We're taking the statics right here. That's what we're doing. Okay, so this is at equilibrium. Glad I went over this. So we're going to take this at C, and even though there's probably not anything in the X direction, I'll put them on here and put the reaction in there. And there might be a little bit. We're really small angles. And we'll write out that we have, we're taking clockwise, counterclockwise is positive. So we can see that the force due to the force of the spring at A, which is going to be negative, cause a negative moment, and that's going to be the K times the static deflection at A times the length, which is going to be the 0.36. And then we're going to see, we're going to also have the, this is going to be counterclockwise, we're going to have mg, and I guess I decided to leave it there as mg, not put the numbers in here, and this distance, which is 0.06. And then lastly, we're going to have this guy, and he too is clockwise, and he's going to have k times del, and call it static of A. And now this is going to be times 600 minus 360, that's 240, so 0.240 equal to 0. All right, so this is going to help us get rid of some of the terms later on, right? And I decided not to bother sticking anything in there, or this is supposed to be B. Yeah, that was supposed to be B, sorry. Because when we go to now do the FBD and IBD, so now it's actually in motion. And I'm making it dip down a little bit further than it was before. And we're still going to have this reaction. RCY, RCX. But now we're going to have, with a large, this is going to have a larger angular change right here. And here is going to be our mg. And over on this side, because we took the moment of inertia about C right here, we can just write IC. And I get, I have it on my page as theta dot. This should be theta double dot. There you go. Must have been something fell apart. Now, this force right here is going to be K times 0.24 times theta, right? So that's going to be the deflection this thing has moved, but also plus the static deflection at B. And then this force right here is going to be K, but now going to be 0.36, sure, 36 theta plus the static deflection at A, right? So there's the deflection, so this is going to be that distance right there with a theta in here, and with a theta in there. So if we take the sum of the moments about C, and I'll still call it the sum of the effective moments about C, so I like that term, we'll have negative K 0.36 theta plus the static deflection times the distance 0.36, right? And then we'll also have, I guess I'll do this one next right here. This is also going clockwise, so another negative K 0.24 theta plus del static B times 0.24, okay? And then we're going to have this guy is going counterclockwise, so plus mg times our 0.06. And then that's supposed to be equal to, on the left-hand side, I made this counterclockwise, right? So we're going to have IC theta double dot. So if we distribute this out right here, we can find this up here is going to be equal to 0. So we can collect all of those guys that are in here and try to find where that's going to be 0. So first off, we go negative k 0.3. Whoops, did I hang up? What happened here? I hate it when that does that. This thing's a piece of crap. I'm not going to use this visualizer anymore. It just hangs up. Oh, seriously? I don't need this in my life, man. How about just Alt-Tab? Something else. All right, and then close this. Is he working? There you go. Now I'm gonna go, let's see, I'll log onto the camera instead. What a piece of crap. I hate that thing. It's just that it used more of the screen than this thing like cuts off like a part of the screen. I don't like that, but at least it's working correctly. All right, so 0.36 theta, I want that one. But that's got to be squared, right? So it's got that squared in there. And then this k 0.24 is getting multiplied here, so we squared theta. But then we bring this other thing out over here, and we go minus k static a 0.36 minus k del static deflection 0.24, and then also plus mg 0.060 equals IC theta double dot, right? And the whole point of this was that this guy right up here was already defined as equaling 0. So that's sort of like the trick of the thing, is to know that you have the static deflections. It allows you to get rid of this gravitational term, which is interesting, I think. And for whatever reason, I didn't put this in, turn this into numbers yet. That's odd. Why didn't we turn this into numbers? I don't know. But anyway, what we're able to get here is theta double dot plus k over IC times the quantity of 0.36 squared plus 0.24 squared theta equals 0. Of course, this is for small angles. We already made that assumption because we just took it times theta. I mean, we did right from right here. We made that assumption that it was going to be a small angle. Otherwise, that would have been sine of theta. But it's a pretty good assumption, as most of the time we're only going to deal with small angles. And so what we're left with here is, plus stuff inside here is going to be 526.2 theta equals 0. Therefore, the natural frequency squared is 526. So we don't need that. We'll just get the natural frequency. All right. So the natural frequency is the square root of 526.2. As a value, that's going to be 22.94 radians per second. But we would rather have the frequency because we were asked for the frequency of vibration, and that always means, unless they say the circular frequency, they always mean divided by 2 pi, so that you end up getting the natural frequency of 3.651 hertz, right? So that's going to be part A to the example. And then part B, they say that the maximum velocity, so V max, is equal to 0.001 meters per second, right? So another way to look at that is that theta dot max is going to be equal to, okay, so that's going to occur right here at this end, right there. So if you want to find the velocity at that S, it's going to be maximum velocity. You could find the maximum angular velocity would just be Vmax divided by 0.36, right? So just dividing out through there, we end up getting, I'm going to turn it into scientific notation because this is, I don't like writing that many zeros. So it'd be -3. This is radians per second. And we know that the general solution of the oscillating position is going to be theta m, this is the magnitude right there, times the sine of omega nt plus phase angle. So the time rate change of this, right, if we're going to take the derivative of this thing, we'd have theta m omega n times the cosine of omega nt plus my phase angle, right in there. So the maximum will occur, right? So the maximum this thing can happen, the maximum of this right here will occur when this is equal to 1, because this will always be a number that's either 1 or smaller. Therefore, the what we want to try to find is we want to find the magnitude of the maximum angle, right? So given a maximum velocity, you want to find the maximum angle. It's sort of a logic thing that we're working through here. So that means, because this right here will be 1, that when this thing becomes a maximum, that has to be equal to 1, that we would have theta dot max, which is this guy right here, divided by the natural frequency. So take our, what you got here? 3.056 e minus 3 and divide by the natural frequency of 22.94, and what you're left with is 1.332 e to the minus 4 radians. And if for whatever reason somebody wanted it in degrees, right? So this is the amplitude of the angular motion of the rod, right? So that's what we were asked for right here. The amplitude of the angular motion of the rod. And they want angular motion, right? So we could even find if we wanted to get what the maximum motion was, and that would be taking that angle and multiplying it by this length, and that would tell you what the maximum would be. And I turned it later into degrees, right? So just for your edification, which is a great word, that'd be 7.63 e to the minus 3 degrees. All right, so that's too long of a video, that example, longer than I want to do. We'll see how efficient I can be in class, or I could just say watch the video. That's not right.